All right. So this is the thing that I'm going to do in this video is give a rigorous attempt to explain a rigorous proof of why standard deviation is divided by n over 1 instead of by n. Excuse me, why variance is divided by n over 1 instead of n, which is, of course, goes into standard deviation as well. And so the thing that we're going to start, the way this is going to work is I'm going to start with some axioms, some definitions, basically. These are in purple. Yeah, maybe I should describe this how this graph works. All right, so there are a few colors here. Purple is for definitions. So these are how we're defining things. Green is the linguistic description, so describing in words what the equation that it's next to means. Yellow is most of the doing out the math just by substitution or factoring or whatever. And blue is describing what any given edge or arrow is. So this tells us what move we're doing, why this is legal. And our goal is to start all the way from these definitions, and then we want to get to an analytic expanded form of our sample variance. So we're going to see that sample variance has an extra n over 1 in the sample variance equals n over 1 over n times sigma squared. That is 1 over n minus 1 over n times the population variance. And so in order to adjust for that, in order to make our estimator be an accurate estimator, an unbiased estimator of population variance, we'll need to adjust by n over 1 in the denominator. Is that correct? Do I have that right? Looks like it. Okay. So to start with, just going to zoom in here. The first thing is we're going to define mu. Mu is the population mean, and it is defined as the expected value of a random data point drawn from the population. So every time we, so mu is the actual true mean of the population, and because of the definition of expectation, we know that that's the expected value of is if you take some random point, it's going to be equal to the mean of the population. We also have defined the variance. Sigma squared is equal to the expectation of xi minus mu squared. So one thing here is that xi is a variable. It's standing in here for a specific draw. Excuse me, that's not right. It's standing in here for a particular draw, but we're not committed to any particular value for that xi. It's a variable. So the variance, sigma squared, is how we say variance. Because sigma is standard deviation, and standard deviation is the square root of variance, so variance is sigma squared. The variance is the expected difference between a point and the mean squared. So for any random point, we pick a random point, we subtract the mean from it, and we square it. And remember, I explained in a sort of hand wavy way why we square our deviations in a previous video. And the expected value of doing that operation, not an actual value, but the expected value of doing that operation is going to be equal to the variance. That's what we mean by variance. That if we do this procedure many times, and in the limit of doing this infinite many times, taking a random point, subtracting the mean from it, and squaring that, and we take the average of all of those variables, excuse me, we take the average of running that procedure many times, we're going to get sigma squared. I'm also going to just so those are the two definitions that we're starting with. And the next thing that we're going to do here is just follow this branch. Where what is happening in this branch? We are trying to get ultimately to the expected value of xi squared, which is going to be important for substitution later. We want to do it now. No, let's jump over to these. All right, so those are two definitions. That's what mu is equal to the expectation of a random draw from the population, or the population mean is equal to a random draw from the population. The population variance, importantly, the population variance is equal to the expectation of the squared deviation of any given point. So we're going to define two other things that are two other pieces here, which are sort of parallel, and these are sort of naive estimators for the mean and the variance. So we have the mu hat, we have mu hat, or we might call it the sample mean or pseudo mean. And this is just our sort of naive notion of how we can estimate what the true mean is from a given sample. So we're going to take n data points. N here means the number of data points that we're taking in our sample. This n, and also throughout this proof. And we're going to take a sample of n data points, and we're going to run both this mu hat and also this sigma hat squared. I wonder if that should be sigma squared hat. I guess it doesn't really matter. We're going to run this with these estimator procedures, and these are sort of our naive, like, first thought about how we might be able to get at the population mean and population variance using the sample. So we talked about mu hat in the previous video. The sample mean, or pseudo-mean, is equal to the average of all the points in the sample from x1 to, this should say, xn. So we're going to take all the xi's. We're going to sum from x1 to xn, and then we're going to divide by n. So it's just an average. So we're taking all of the points in the sample and we're averaging them. This is pretty intuitive, and we can show that this is unbiased. So the thing, this leg of the proof is trying to show that the expected value of mu hat is equal to mu. Note that doesn't mean that it is going to be exactly equal to mu, just that in expectation it's going to be equal to mu. We're as likely to be, assuming that the sample is assuming that the population is symmetrical, we're as likely to be, the mu hat is as likely to be above mu as it is to be below mu. And if the population is not symmetrical, then we still have a sense that the deviation, the average deviation is still going to, of any given mu hat, so is going to be, if we take a bunch of mu hats, the deviation, and we add up all the deviations of those, all of the deviations from the mean of all of those that are above the mean, and all of the deviations from the mean of all those that are below the mean, we'll find that those are equal, right? Because we might have a distribution with one really far out outlier, and it only gets added into, for instance, and it only gets brought into a sample very rarely, but when it does, it makes that sample, say, the mu hat of that sample just much greater than the population mean. That sort of sample sort of becomes an outlier, but that's sort of balanced out by having most samples not include that outlier, and accordingly, because they don't include that outlier, they're going to be they're all going to be somewhat smaller than the population mean. So how do we prove this? Well, the expectation of mu hat, so right here we're just taking the expectation of both sides, which we can definitely do. And because expectation is linear, and this is pretty important, we can pull out the 1 over n. So expectation is linear because it is technically defined as an integral. We're actually integrating over okay, actually I'm not super clear on that. It's an integral under the hood. And so we can just treat each individual, we treat it as linear, because just like because expectation is technically an integral. I'm not specifically clear on exactly how we would define it. I think in the limit of, I'll have to think more about that. But because it's sort of under the hood and integral, that means that we can take all of the added terms, and just like when you're taking an integral and you have the integral of a plus b, that's equal to the integral of a plus the integral of b. And if you have a constant c, c times x, you can always take out the constant. So the integral of c times x is equal to c times the integral of x. So the thing that we're doing here is we are taking out the 1 over n, because n is a constant. It's not going to change, or rather, at least in this procedure, but for this whole proof, we're holding n constant. It could be any. It is a variable. It could be any number, but it doesn't change throughout the scope of this proof. So 1 over n is a constant, whereas xi is not a constant, because this summing procedure is sort of calling xi over and over and over again. And so we're going to have actually n n different xi's, and so meaningfully, that's like a xi is sort of like meaningfully a variable in this context where 1 over n is a constant. Because expectation is linear, we can distribute it to all of the sum terms. So we were just talking about that. We can think of this. We can think of this sum as x1 plus x2 plus x3 all the way up to xn, and so we can just treat each of those. Sorry about the noise. All right, hear me? So because expectation is linear, we can distribute it to all the sum terms. So instead of the expectation of x1 plus x2 plus x3 to xn, we have the sum of the expectation of x1 plus the expectation of x2 plus the expectation of x3 all the way to xn. And then we can substitute for because mu is equal to the expected value of xi, we can just substitute in the population mean in for the expected value of xi. Remember that we're summing all of these different xi's, but each one is a random draw. Each one is as likely to be, each one is on expectation equal to the population mean, even though if we were actually doing this procedure, we would have a bunch of different values for each x, and they would each vary from the mean, deviate from the mean by differing amounts, but the average deviation would be 0. Yes, the average deviation would be 0, but not the average squared deviation, which is why we're able to measure variance at all. But the average deviation will be 0 by definition. Okay, so summing a term x n times, then dividing the result by x equals, dividing the result by n equals x. So we have this averaging basically, 1 over n. So here, because mu is a constant, we're summing from 1 to n. That's just multiplying mu by itself n times, right? We're saying mu plus mu plus mu plus mu all the way to n terms, and then also we're dividing by n, or multiplying by 1 over n, and so this summing and this dividing cancel out, and we end up with mu. So the expected value of the pseudo mean is equal to the average of all the points in the sample, which in expectation equals the population mean. One moment. How do you spell pseudo?
There are two words pronounced like that. P-S-E-U-D-O.
Yeah, so the expected value of the pseudo mean, where's the E? Pseudo mean. How do you spell pseudo?
There are two words pronounced like that. P-S-E-U-D-O.
No.
Or P-S-E-U.
Okay. The expected value of the pseudo-mean is equal to the average of all of the points in the sample, which in expectation equals the population mean. So great. So that means that mu hat is an unbiased estimator. In expectation, it's the value of mu hat equals mu. But there's another question that we might ask here, which is what is the variance of mu hat? Which, if we follow this dotted line, is the question we're asking over here. So we know that mu hat is an unbiased estimator of the population mean, that on average, the value of mu hat will be equal to mu, but we might also be interested in the variance of mu hat. If we took many samples of mu hat, how spread out would they be? Like, we could imagine that we take a bunch of samples and they are pretty clustered together, or we can imagine that we take many samples and they're pretty spread out. Like we have the population graph, and then we have a bunch of sort of little humps that each represent the different samples. So we calculate this using the definition of variance and treating each drawing of the pseudo-mean as a data point. So the thing that we're going to do here is we're going to import the definition of variance, but instead of it being the case that we're going to estimate the variance of the whole population of each xi, instead xi is going to be mu hat. So we're going to treat each sample mean as a data point. So basically that procedure means we're going to take n data points, we're going to average them, we're going to get a sample mean. We're going to use that sample mean, and we're going to subtract the population mean from it and square that. That's one round of the procedure, and then we're going to do that over and over and over and over again with different samples and therefore different sample means. So we're finding the variance of those sample means. And so we start with the expectation of mu hat minus mu squared. The squared is inside the expectation. And then what happens next? Mu hat minus mu squared. Well, we're drawing in something from over here. We're taking mu hat. It looks like we are just substituting in the value of mu hat. But we are missing a parentheses. There, all right, so that, nope, we are not missing a parentheses, but we're gonna add an extra one. All right, substitution. All right, so we know the value of mu hat. It's just the average of all of these points from x1 to xn, and we're just going to substitute that into our expression here. And the next thing we're going to do is a little bit strange. We're going to take this mu, and we are going to sort of put it inside the sum. I actually don't want these parentheses because we don't need them because it's multiplied, and PEMDAS multiplication gets done before subtraction. So we have this sum, and outside of the sum, we have this single term mu. Now, normally, we couldn't, if we were to take a constant and we were put it inside of a sum, that would be as if we were multiplying the sum, multiplying that by multiplying that constant by n times, right? Because we have x1, we have x2, we have x3, and we're going to turn that into x1 minus mu, x2 minus mu, x3 minus mu. Oh, actually, these are yeah, and that would be like adding in a bunch more minus mu's, where currently we have one. However, you could compensate for that by just having on the outside multiplying by the same number of positive mu's. Or in this case, not multiplying by the same number of positive mu's, adding adding mu multiplied by the same factor. Or in this case, we're canceling because we have this 1 over n. So we're putting mu into this sum, which is sort of equivalent to multiplying it by n. But as we're doing that, we're also putting it into the bounds of this 1 over n, so it's also being divided by n. Those two cancel out, so this is a legal operation. So we do that. Now we have the expectation of 1 over n times the sum of xi minus mu squared. We can distribute the square across the multiplication. So we have 1 over n squared times the sum of xi minus mu squared. 1 over 2n is constant and has a constant expected value, so we can pull it out of the expected value. So this is the expected value of 1 over n squared is just equal to 1 over n squared. So we factor that out, and then we expand this sum. Important. We are keeping this xi here. We're renaming xi into two variables, xi and xj. Both of these are independent draws from the population, but I'm giving them two names just as a way to remind myself that that they're not equal. That there's a possibility, of course, that xi equals xj, but they're both random draws. It's not the case that I can just treat them as equal. They both have some possibility of being that they are equal in expectation, but they represent different separate draws. Okay, and so here's some of the tricky part, which I actually laid out in a different video with the whiteboard. So if we substitute yi for xi minus mu, so we're taking those two terms and we're sort of combining them into a single term, just because that makes it easier to think about. So yi equals xi minus mu, which means y1 equals x1 minus mu, y2 equals x2 minus mu, all the way on until yn equals xn minus mu. We can think of the result of this of this multiplication as an n by n matrix of terms that are summed together. Specifically, this multiplication. Whoops, that's not what I wanted. Right, so for every term, so this becomes yi times yj. Excuse me. This becomes the sum of yi times the sum of yj. And so for every so for I equals 1, we're going to take the first term in this sum, and we're going to multiply it by every term in the other sum. So that's y1 squared, y1 times y1 plus y1 times y2 plus all the way on to y1 times yn. And then in the next row, we're going to take y2, and we're going to multiply y2 by every term in this other sum. So y2 is equal to y2 times y1, y2 squared until y2 times yn, and until finally we get to all the way down to the bottom, and we have yn times y1, yn times y2, until we have yn squared. If I were tutoring someone, I would check in to make sure this makes sense now. It seemed a little confusing to me at first. We summarize this as the sum of all of the diagonal squared terms plus the sum of all the non-diagonal unlike multiplication terms. Crucially, these terms must be unlike, and we do not sum any of the cases where I equals j, because those cases are already covered by the sum of the squares. We separate them like this because these should be treated differently later. So a thing that we're noticing here is that we have this 9 by 9 matrix, which is basically just a really long ass sum. A sum with 9 squared terms, and along the diagonal of this matrix we have squared terms. So here we have y1 squared and then y2 squared all the way down to yn squared, and that is different. Those are different than these unlike multiplied terms where y1 times y2, for instance. And we can treat those differently. So we have I'll remember all of this is in an expected value. We're going to factor those out. So the diagonal terms look like the sum of all of xi minus mu squared, right? Remember, we're converting back from thinking from yi into, maybe we should do it with yi first. So we have the sum of yi squared from y1 to yn. So that's y1 squared, y2 squared, y3 squared, y4 squared, all the way down to yn squared. But we're converting that back into xi minus mu, and so we have the sum of xi minus mu from 1 to n. Excuse me, the sum of xi minus mu squared from 1 to n. In fact, just to clarify, I'm going to add some parentheses here. The squaring is inside the sum. And that's one term, that's all the diagonals. And then separately, we want to have the sum from sum of I going from 1 to n, and from j going from 1 to n, where I does not equal j. And we're factoring out where I does not equal j because that's already covered by this term, and we're just multiplying those together. So that's all of the other non-diagonal terms. So the first sum, so that's y1 times y2 plus y1 plus y3 plus y1 plus times y4, and so on, and then also including y2 times y1, y2 times y1 plus y2 times y3, and that's what's going on in the second term. And then, because expectation is linear, we can take the expectation of all of the terms in the sum and add those expectations. Because expectation is linear, we can take the expectation of all of the terms in the sum and add those expectations. Right, so we're now just factoring the expectation. So here it's outside of the sum. Now we're factoring it into the sum. Actually, okay, I'm not as sure. Okay, yeah, the expectation is inside of these sums, but notice that there's only one expectation for these two things that we're multiplying. It would not be correct to take the expectation that the multiplying two non-constants, the expectation of a variable times variable is not necessarily equal to the expectation of the variable times the expectation of the other variable. All right, so in expectation, the deviation of the so now we're just dealing with this second part, which is equal to 0. So why is it equal to 0? So in expectation, the deviation from the mean is 0. So both of xi minus mu and xj minus mu, so the expectation of both, the expectation of both xi minus mu and xj minus mu is 0. Another way to think about this is each term could be positive, each term could be negative, or one could be negative, one could be positive. The double negative case and the double positive case cancel out. They cancel each other out. That is, like, if it could be that x. All right, so say it a different way. For any given pair of xi and xj, it could be that xi is it could be that xi is positive, could be that xi is greater than mu, or it could be that xi is smaller than mu. Same with xj. Could be that xj is bigger than mu. Could be that xj is smaller than mu. If one is bigger and one is smaller, again, this is not strictly rigorous. Then those two cancel out. Obviously, they need to have the same magnitude, but there is likely to be their average deviation is also 0. And so we're expecting that in any given role here, that xi might be a little bit, xi times xi minus mu times xj minus mu might be positive, might be like a good deal bigger than the mean, but it's as likely to be bigger than the mean as it is to be less than the mean. And so overall, across the sum, this cancels out. Not across the sum, across the expectation, this cancels out. Like as we do this operation infinitely many times, we end up with an expectation of 0. So we're summing this to 0. Then we're going to simplify. The only thing that we are doing here is taking out the 0. And so now we have mu hat minus mu squared. Right, so remember the variance of our samples is equal to 1 over n squared times the sum of the expectation of xi minus mu squared. And we know that sigma squared is equal to the value of xi minus mu squared. Right, we defined that all the way up here. So we can just substitute that in. Instead of xi minus mu squared here, we have sigma squared here. So 1 over n squared times the sum of sigma squared. Again, because this is a constant, the sum of sigma squared up from 1 to n is just the same as taking that's just sigma squared plus sigma squared plus sigma squared plus sigma squared n times. So that's sigma squared times n. And then we can simplify. These seem like they're out of order. We simplify, and this n cancels out with one of the n's in the denominator here, so we end up with 1 over n times sigma squared. So the variance of mu hat, if we take a bunch of samples and take sample means for all of them, so we get a bunch of sample means, and we measure how much do they vary. The variance of those sample hats is equal to 1/n of the variance of the population. All right, so that is about half of the proof. That's actually just laying the groundwork. The next thing that we want to do is go back to our definition of sigma hat and show what get to an analytic value of what sigma hat is.